Hello everyone, thank you for joining me in this particular video. So I'm going to continue from the last video where I said I will be implementing the CNN architecture which I showed you at the end of the video. So let us begin. So first of all, I want to import TensorFlow. I also want to import matplotlib. So the architecture I'm going to implement is found in this particular folder. So let us view the architecture. I'm going to first read the image of the architecture, then after that I'm going to view it. So let me specify the image size. So I'm going to use image size of 24 by 20. So and then I'm going to disable the axis, and then I'm going to now view the image. Yeah, so we see that we are going to need the input, the convolutional layer, the max pooling layer, and the fully connected layers. So first of all, let us import the functions that we need from TensorFlow. So from TensorFlow.keras, I need the input, where I will specify the input shape. Then I also need the sequential. This sequential allows us to stack layers on top of another in order to create a TensorFlow model. Then from the TensorFlow layers, I also need the convolutional layer. Now these layers that are importing are high level. So during the initialization of a convolutional neural network, the weights of the shape of the filters are randomly initialized on the first instance, and then during training is where now the weights will be changed according to the pattern that is being learned in the images input into our model. So as opposed to low-level implementation of the convolution operation, in this case now we don't specify the weights of the filters. In this case now, the weights of the filters are randomly initialized, and then during training they are adjusted according to the patterns learned during the training of the model. So thank you. So now that we've imported the requirements that we need, let us create it. So first of all, we see that we need an input of shape 227 by 227 by 3, and then after the input, see now we need a conv2d composed of 96 filters, and then we see that the size of the filters are 11 by 11, so we can put it as a single integer to mean 11 by 11, or we can put it as a tuple of two values, but either way it's fine. So I put it this way. Then we see that the strides required are 4. And then I'll also implement an activation as the output. In this case I'll use relu. Since there's no padding, so we leave it at that. So in this case the padding is just as equivalent as valid padding, which is the default padding, which essentially means there's no padding in this layer. So after the convolution, then we have the max pooling layer. We see that the pool size is 3 by 3, and the strides is equals to 2. So after that, now that the first layer is complete, then we go to the second layer. Now we see that in the second layer the depth is 256. We have filter 5 by 5, and then we have a stride of 1 and a padding of 2. So earlier on in the last video we saw that the padding which were available were valid and same, and we say that valid essentially means that it's no padding, and same means that it's the input size of the convolution will be same as the output size of the convolution. That is now for a stride of 1. But now in this case there is a specific padding required for this kind of layer, so that's why we are going to use the 0 padding 2D layer in order to specify the padding that is required for that layer, which is equal to 2. So now we see that the second layer's depth of 256, kernel size 5, stride 1. I've also used activation relu. Then max pooling is 3, stride of 2. Then after that, now we finished with the layer 2, and now we are going to layer 3. So conventionally, okay, in most scenarios, a convolution and a max pooling is always considered one layer. So that's why when I talk of layer 1, I include convolution and max pooling. Layer 2, also the convolution and max pooling. So when you see from layer 3, 4 and 5 are all convolution layers. So let me implement them. So first of all I copy here. So layer 3 has a padding of 1. So change this one to padding of 1. Then you see that it's a depth of 384, stride of 1, filter size 3. So here is 384, kernel size 3, stride of 1, copy, and then when I go to layer 4 also, we see that it's 384, depth of 384, stride of 1, pad of 1, filter size of 3. Then also for layer 5, we see now the depth has gone down to 256. So for layer 5, now the depth has gone down from 384 to 256. So now again, now from the fifth convolution, we now have a max pooling layer. So which is a filter size, which essentially pool size 3 by 3 and stride 2. So we just copy this one and put it there, since essentially that's what is done. And then now from the max pooling, we go now to our fully connected layer. So in this case, from the max pooling, as I said in the earlier video, that when we are going now from the max pooling to the fully connected layer, we'll first do a flattening of our input to the fully connected layer from a matrix to a vector. So in that case, I ought to have also imported a flatten here. So before I go to the fully connected layer, I do a flatten. Then after doing a flatten, now I go to the fully connected layer, of which the first layer has neurons 496. So as neurons 496, and then let me use activation as ReLU. The second layer also has neurons 496, and I use the activation as ReLU. And then the last layer, since the CNN architecture that we are implementing right now was being used to predict the ImageNet 1000 dataset, which has 1000 clauses for classification. Now the output is now 1000, and then the activation that we are seeing being used is the softmax activation function. So essentially now we've fully implemented the convolutional neural network that we have shown above. So now this is the implementation. Yes, so when I run it, yes, I've implemented it. Now we can view the properties of the model that we implemented. So in this case, we can see the summary of the model. We can see each layer, the output shape, and the parameters. So essentially the max pooling layer has no trainable parameters, so that's why the parameters are 0. So essentially the parameters for the convolutional neural network are there because convolutional neural network has trainable weights. And also, apart from the convolutional neural network, we also see that the dense or the fully connected layer has trainable parameters, from which now the convolutional neural network learns and then adjusts the weights according to the patterns being learned in our model. So we can further also adjust the names of the layers, such that we can say this is the input layer. We can also do this for the other layers, such as we can also do so for the other layers, such that if you want the names that are shown here to be your own custom names, you can do that. Sorry about that. So like for these names, you can do that using the name argument passed through each layer. And then the same goes for the model. If you want to change the name of the model to your own liking, you can pass here the name of the model. So that now the name of the model that we see here will now be CNN model. So yes, so apart from viewing the summary of the model, we can also see the loop through each layers and see the name. So for layer in model.layers, we can view the layer name using the .name argument. We can see the input shape to a certain layer. We can see the output shape. Then apart from the output shape, we can also view the number of parameters in the layers. So when we run this, we'll see all those properties per layer. So we see the name, the input shape, the output shape, and the model parameters, the number of parameters. So also the same for the general model. We can be able to view the model name, the model input shape, which is an image of says 27 by 27 by 3. So by 3 essentially means it's an RGB image. Then we can view the output shape, which will now be at 7 by 7 by it will be 1000. It will be 1000. Then we can also see the total parameters in the model. So you see that it's the name for now is a sequential model. Then the input is none by 227 by 227 by 3. So the none essentially implies the batch size, which for now, since the model does not know the batch size that should be specifying for the data being input into the model, for now it's none. Then the output is none by 1000, essentially meaning the outputs will be in batches of which will be specified during model training, and then over 1000 classes. Then we see the total parameters which will be trainable during the model training, which will be almost 62 million. Then yeah, so apart from that, so there is a way in which we can know the number of parameters and calculate the number of parameters that is essentially found in the trainable layers of a model, and also the way we can calculate the shape that will be in the next layer of a of the model. So due to this, let me introduce a certain concept which I learned in Andrew Ng's CNN course in Coursera, which the link to the course I'll input below. So in the CNN course by Andrew Ng, this was the question: if you have 10 filters that are 3 by 3 by 3 in one layer of a neural network, how many parameters does that layer have? Does that layer have? So essentially, in this case scenario, the filters are 3 by 3 by 3. So the last 3 corresponds to the, for instance, if the input shape accepts images of grayscale values, so of grayscale of RGB channels for the last 3 of the filters, then the filter will automatically be 3 in the in the last dimension. But if the images were grayscale, then it would have been 3 by 3 by 1. So the last dimension of the filter is inferred from the input to the model. So in this case, since our model, for instance, was 227 by 227 by 3 in its input shape, so the last 3 will be inferred, and then the last dimension of the filter will also have a 3. So in this case, the answer was, first of all, the number of parameters will be the dimensions of the filter, then plus a bias, of it the bias will be a 1. So in this case it will be 3 by 3 by 3, which will be 27, then plus a bias of 1 will be 28. So essentially this will be for one filter. So for each filter there's a bias. So in this case, since we are calculating the number of parameters for a single filter, the bias is 1. And since we know that we have 10 filters, so it will be 28 by 10, which will now be 280 for the 10 filters. So essentially now this is the way to calculate the number of parameters. So in general, the formula for calculating the number of parameters for convolutional layers, we take the filter dimensions, we multiply by the filter dimensions, then we take times the number of channels for the previous layer, and then we take times the number of channels for the current layer, and then we add by the number of channels for the current layer, which will essentially be the number of filters which are going to be created for that specific layer. So for instance, if we wanted to calculate the number of parameters here for the first layer, for the convolutional layer, what you do is take 11 by 11 and to take by the number of channels for the previous layer, which is by 3. So it will be 11 by 11 by 3, and then we multiply now by the number of channels for the current layer, which will be by 96. Then after that we add plus 96. So 11 by 11, that would be 121. Then we multiply by 3, that will be 363, and then we multiply by 96, then we add 96. So that will be 34,944. So that goes the same for the convolutional layer in the second layer. So in that case, for the convolutional layer in the second layer, we take a 5 by 5, and then we multiply by the number of channels in the previous layer, that by 96. Then we multiply by the number of channels in the current layer, that will be 256, and then we add the number of channels in the current layer, which will be equivalent to the number of the filters that will be formed. So we add 256. So that will give us 614,656 parameters. So that's how we can calculate the parameters of the current of a convolutional layer of a convolutional neural network. And then for the case for the dense layers, so for the dense layers, for the dense layers, what we do, we take the number of channels in the current layer and then we multiply by the number of channels in the previous layer, and then we add the number of channels in the current layer. So for instance, when we go here, for instance, if I take the first dense layer, now I take the number of channels in the current layer 1496, I multiply by the number of channels in the previous layer, which is 256, then I add the number of channels in the current layer, that will be 1496. So when I calculate that, I get the number of parameters as so I take 1496. Oh, sorry about that. Let me do for the second dense layer. So it will be 1496. Then I multiply by the number of channels in the previous layer, 1496. Then I add in the current layer 1496. That will be 16,791, 312. Then for the dense layer in the last part, what I'll do is I do 1,000, then I multiply by the number of channels in the previous layer, then I add the number of channels in the current layer, which is 1,000, so that I'll get 4,097,000 parameters. So I guess the reason why the first dense layer did not give me the results as expected was because the flattened the inputs to a vector, so it changed the dimensions. Then after flattening, now remember there was a convolution here, and then there was a max pooling here. Then after the max pooling, now the matrix output shape which was found after max pooling was flattened to a vector. So now the vector dimensions are now what will be used as the number of channels coming out from the previous layer, which are now the length of the flattened elements will now be the number of channels coming out from the previous layer. So apart from that, I also want to talk about how we can calculate the output shapes per layer of the model. So we know that the output shapes are affected by first of all, they are affected by the number of channels, the number of channels of the previous layer, the padding done, and the size of the filter, and also the stride. So if you want to calculate the shape to a certain the output shape of a certain layer, or the input shape to a certain layer. So in this case, for instance, if we want to calculate the input shape that we'll get in layer 2 from layer 1, what we do we take the number of channels of the previous layer, then I multiply by the number of the padding that will be done in that current layer, so which is multiplied by 2. Then after that I subtract the filter, then the all of this computation I divide by the stride of that current layer, and then the all of this computation I add 1 to it. So this is the way we can do the number of channels, then the size of the matrices that are entering a current section. So for instance, for the output shape of layer 1, the output shape of the convolutional neural network that will be going to the max pooling of layer 1, essentially how we do it is we take 227 here, and then since there is no padding in the first layer, this one will be 0, then it will be minus 11, then since the stride of this convolutional layer is 4, now that one will be 4, it will be 4, and then the all of this, then we add a 1, so it will be 227 plus 0 minus 11 over 4, then we add a 1 to the all computation here. So when we do the result of our operation, we get plus 1. So we get now that the input shape to the max pooling will now be 55, which is the correct one. And then the pooling shape, since it's pool size 3 by 3, stride of 2, it will reduce it by essentially by half, and we see that now it's kind of like, since this is odd, now it's kind of like truncating the results. So the same can be done to the other layers, essentially the convolutional layers of our CNN. So I've talked about how we can create the architecture of a CNN, implement it, how we can view the parameters, the name, the shapes, and also how the parameters of a convolutional neural network are gotten for both for the convolutional layers and the dense layers, and also how we can get the shapes of every layer of a CNN. So thank you for watching, and I'll see you in later videos where we'll be seeing how we can do training of the convolutional neural network on the CIFAR dataset, CIFAR 10 dataset, and also how we can implement various CNN architectures such as the GoogleNet, the ResNet, the AlexNet, and so forth. using TensorFlow. So thank you for watching, and we'll meet in the next video.